Hello, I'm Bernd Brach and I'm presenting our paper, One Lipschitz Layers Compared, Memory Speed and Certifiable Robustness. This work was done together with Fabio Brau and our supervisors, Giorgio Butazzo and Christoph Lampert. In our work, we analyzed and compared existing methods of parameterizing one Lipschitz convolutions. The comparison we present is based on multiple different properties, including both theoretical as well as empirical ones. Current image classification models are not robust. Tiny, invisible perturbations of the input, known as adversarial examples, can change the predictions of the models. The existence of adversarial examples could lead to users not trusting the models. It could be a security issue, and it also makes it impossible to build interpretable models. Therefore, we think it is important to have models that are free of adversarial examples. In order to create classifiers that are guaranteed to be free of adversarial examples, many recent works have proposed methods of parameterizing one Lipschitz networks. We call a function, a layer, or a network one Lipschitz if the difference of two outputs is at most as big as the difference of the corresponding two inputs. We usually build up one Lipschitz networks by stacking multiple one Lipschitz layers. When classifying an image using a one Lipschitz network, by construction, any perturbation of the input image can change the output of the network by at most the same amount. Therefore, if the difference of the largest two class scores of the original image is large enough, we can be sure that no perturbation of certain magnitude can change the order of outputs, and therefore the prediction of the model. Recently, various methods of parameterizing one Lipschitz convolutions have been proposed, and it is not clear from previously existing literature what advantages and shortcomings different methods have. Therefore, in this work, we analyzed 7 popular methods and compared them in terms of memory requirements, throughput, computational complexity, accuracy, as well as certified robust accuracy. In our theoretical analysis, we have found that all methods are at most a constant factor worse in terms of floating point operations for processing the input. However, most layers require some transformation, for example, orthogonalization of the parameters beforehand. This transformation usually scales like c cubed for c the number of channels. For Cayley and Lott, this additional term also scales with the input size, making those layers less feasible for larger models. In terms of memory required to store parameters, as well as the activations in the forward pass, most methods again are at most a constant factor worse than standard convolutions. Only Cayley and Lott require memory that could be much larger. For empirical evaluation, we compared the 7 methods using 6 metrics on 4 datasets with 4 architecture sizes and 3 different time constraints. We first compared training and inference times, as well as memory requirements at training and inference time. Results are generally in line with our expectations from the theoretical analysis. For example, we can see that models using AOL and SLL require not much more time for an epoch with the XS-sized model, but for larger model sizes, the C-cube term eventually does have an influence. In terms of training memory requirements, we see that some methods require vastly more resources than other models, making them impractical to use in larger models. We also compared accuracy and certified robust accuracy obtained by networks using different one Lipschitz convolutions. As shown in the previous slides, different methods can require very different amounts of time to process one epoch. Therefore, in order to compare methods fairly, we did not restrict the number of training epochs, but instead restricted the training time. We found that in general, the method SOC, here shown in pink, performed very well, in particular for the low-resolution datasets. Also, the method CPL, here in green, usually was among the best methods. Overall, we believe that CPL is the most promising method due to high performance and low consumption of computational resources. With larger resources available, SOC seems like a good alternative. Finally, in cases where inference time is the crucial property, AOL and PCOP might be useful, as they do not introduce any additional overhead during inference compared to a standard convolution. In our work, we compared different existing methods of creating one Lipschitz convolutions. One commonality between well-performing methods that we have found is that they all either include some sort of skip connections, CPL, SLL, and SOC, or initialize layer as the identity map, like AOL and LOT. We also found that, as expected, doing computations on the kernel instead of on the full input is an advantage when scaling up methods to larger input resolutions. Interestingly, we did not find a large difference between layers that strictly enforce orthogonality and more general ones. Furthermore, slow methods did not seem to perform worse than faster ones, with SOC and LOT 2 relatively slow methods among the best ones. We believe that SOC and especially CPL are among the most promising methods for constructing high-performing, Certifiably Robust Models in the Future. Please find more information and further details in our paper, One Lipschitz Layers Compared, Memory, Speed, and Certifiable Robustness.